Okay, thank you. Well, first of all, I would like to thank you for inviting us. I've been here already one time before, 4 years ago, I think, and it was really a great pleasure to be here at the time, so I'm really happy and excited that you decided to invite me again. Iran is a beautiful country. Last time we visited Isfahan, this time Shiraz. Of course, Tehran is also very nice, so we're really enjoying ourselves, and well, thanks again for inviting us. And well, I hope you will enjoy our lectures as much as we enjoy visiting your country. So I understand that you already had 2 days of lectures before this, so you have some background in computational geometry. I guess some of you are perhaps even already doing some research in the area yourself. So I hope that I can still tell you something new, but well, we'll see. So what I decided to do this time is to talk about some, well, maybe fairly old in terms of computational geometry, old techniques, but I think it's very important when you're working in this area that you know all these techniques, because essentially, well, almost every problem that you work on, it might actually happen that you need some of these techniques to solve these problems efficiently. So I'm going to do some, well, let's say advanced basic techniques, you could say. So it's basic in the sense that you can apply them. They are applicable in many situations. And, well, it's advanced because maybe if you just take a first course on computational geometry, possibly you did not see those techniques. So it's mainly two topics. One is partition trees and what you can do with them. So that's the first 3 days, and then 2 days about arrangements. And there's actually also, when I talk about applications here, maybe I will need some of the techniques from the partition trees and so on. Okay, and please, if you have any questions, just ask during the talk. Don't wait until the end. Right? It's I'm trying to make it, well, hopefully it will be clear to everybody, but as soon as something is not clear, just ask, and well, I'll try to answer your question. So I'll start with a very short introduction into geometric data structures, and then we'll move on to partition trees. So I guess in the past 2 days you already saw some geometric data structures. So there's a lot of different structures. Maybe you did point location, right? So you're given a planar map. Let's say a map of Asia, for instance, with all the countries, and then a user is going to click somewhere, let's say somewhere in Iran, and then the system has to tell you, okay, if you click in this country, this is Iran, or if you click here, this is Turkey, or the Netherlands, or... well, they're very nice data structures for this. Range searching, so that's actually what we'll be talking a lot about the coming few days. So you have, let's say, a set of points in the plane, and now given a range, which could be a triangle or a rectangle, report all the points inside the triangle, or count how many points are there inside a triangle, or something like this. Ray shooting, a problem that is very relevant for computer graphics. You are given a set of objects, an array, and you want to find out quickly what is the first object, or maybe the first facet of the object hit by a query ray. Okay, so there's lots of different of these data structures, and many of them... Okay, welcome. So many of these are useful just as per se. So for instance, point location is something that you maybe just want to have in your system. that the user directly asks a point location query, but sometimes also when you actually are solving a completely different problem, you can use these data structures as kind of a, well, subroutine or something that your algorithm can use to solve a different problem. So I guess a good knowledge of data structures and how you can apply them is well, something that every computational geometry person should have. So today we'll be talking mainly about range searching. So in general, you could say, what's the range searching problem? Okay, you have a set of objects. Those could be points, or they could be segments, or, well, anything in 2 dimensions, or in 3 dimensions, or maybe even higher dimensions. And now you want to store these in a data structure such that if you come with a query range, okay, so the range could be a rectangle, or maybe a half plane, or a triangle, or a disk, or in 3D it could be a sphere. Then you can either want to report all the objects that lie inside the range, or maybe you want to count how many there are. Sometimes it's useful to simply decide, is the range empty or not? Okay, so in terms of counting, you only want to know, is the number greater than 0, or is it actually empty? In case the objects are not points but segments, maybe you want to report everything that is intersecting the range, or maybe you want to report everything that is completely inside. So there's lots of different variants. I think in the past days you looked at this problem perhaps a little bit. So well, there's lots of different variants and lots of different data structures for all these variants. But actually, for many of them, partition trees are the basis. So we'll be talking about partition trees, and we also a little bit about how you apply them to solve different types of query problems. Okay, so let's first look a little bit at the basics of partition trees. So in general, so I'm going to do most of my explanations in 2-dimensional space. Okay, actually, almost everything also works in 3-dimensional or higher dimensional spaces. I'm just going to mention usually the bounds that you get in higher dimensions, but not the ideas are very much the same, so it doesn't really matter too much. So the basic, well, query problem that you study when you look at partition trees is, I have a set of points. Okay, so we think about points in 2D, and I want to store them in a data structure so that you can quickly, let's say, count how many points are, well, let's say, below a line. Or in other words, how many points are contained in a half plane. Okay, a half plane is, well, a part of the plane which is bounded by a line. Okay, so the query is this line, or this line, or this line, and you want to count how many points are below that line, or maybe report all of them. Okay, so first it's always good when you start looking at a problem to maybe first look at a simpler version to get some ideas. So here we're going to look at, I guess, the simplest version, which is what happens in 1 dimension. Okay, so what is this problem in 1 dimension? Well, I have points now in 1-dimensional space. A half space is simply, well, everything, let's say, to the right of a point here. So I want to count or report all the points, let's say, to the right of this red point here. So how would you do that? Well, a binary search tree, for instance. Okay, very easy. So what we're going to do is we're going to look a little bit at how this binary search tree works, and then see what are the basic ideas behind it, and then see whether we can actually use those ideas also in two-dimensional space. So here's a binary search tree. So if I want to report or count everything to the right of this point, okay, what would you do? Well, this is my point X, so I search with my point X in the tree. Okay, so that's the red path. And now all the points to the right are, well, they are here. So one way of looking at it, it's, well, you have this leaf where the search ends. So that leaf could be inside or not. But it could also be that I search here and then maybe I also end up here. And all the other ones, well, they are the leaves to the right of this. And as you can see there, you can say they're kind of grouped into a number of subtrees. Okay, so in this case, 2 subtrees, this one and this one. So normally the maximal number of subtrees you need to, well, let's say express or to capture all the points to the right of a query point is at most log n if the tree is balanced. Okay, because what is the property of this subtree? Well, if you follow the path and I take a red node, so a node on the path to X, then if the path goes to the left, then the subtree to the right is going to be completely inside our range. Okay, and since the path has log n nodes, if it's a balanced tree, you get at most log n of these subtrees to the right of the path. Okay, so if I want to report all the points, well, it's pretty easy. I follow this red path, and whenever I go to the left, I simply go down in this right subtree and report all the leaves. Okay. What should I do if I want to count those points? Well, of course, I can also go down to all the leaves and count the number of leaves. But then the query time is going to depend on how many points you have here. And then maybe, well, if the path goes all the way here, you spend linear time to count. If you want to report, well, you have to report them, so there's nothing you can do. But if you want to count a number, you can do something more clever. So you have to store a little bit of extra information. So what's the extra information you store? Yeah, exactly. So at each internal node, you store how many points are in this subtree, how many leaves are below this node, and then you simply have to add the number you store here, the number you store here, and, well, you have to check this one if it's inside or not. Okay, so that's log n time. Okay, so this was easy, hopefully. Now let's look at what happens if we want to do this in 2 dimensions. So here, well, I guess it's clear the storage is linear. The time, if I want to report, log n plus the number of k is the number of answers, and for counting it's just log n. Okay, so if you think about it, we have this binary search tree where the points are sorted on x coordinate in a tree. Okay, and for a tree for a search tree we need some kind of ordering. So in 1 dimension this is easy. So, but of course ordering in 2 dimensions, well, is a little bit more difficult, because how do you order on x or y? So what we're going to do is we're going to look at this solution in a slightly different way. So instead of thinking about I have an ordering let's think about it in a different way. So essentially what happens is that, okay, I have my set of points. Okay, they're stored in this tree. And if you think about it, you have the root and you have two subtrees. Okay, so that corresponds to two subsets. The subtree T1 corresponds to these points, P1, here P2. And when you do a query, okay, you only have to recursively check one of the two subtrees, because for the other one, it's always going to be either completely inside the range or completely outside. So if you look at it here, then, well, if I look at it in a geometric way, this point set is contained in this interval. Okay. This point set is contained in this interval. And if I do a query, like here, then you can see, well, for this interval, well, some of the points are maybe inside, some of the points here are outside. So I'm not completely sure points are inside, so I have to go into recursion in that subtree. Okay? This one, everything is inside my range, so I can simply say, if I want to count, well, we know how many points are there, so simply add that to the count that we have. Okay? If this boundary happens to be here, then in this interval some points may be inside and some may be outside. So then I have to recursively go here. But now for this one I know that all of them are completely outside, so I can forget about it. Okay, so in the tree that corresponds to, well, you follow one path down the tree where maybe in this case you say, okay, we go to the left because here we have to go down and do some more searching, but here I know what is going on. So now let's see if we can do this in 2 dimensions. Okay, so here I said I have my point set. I partition it into 2 subsets, P1 and P2. For each subset I have an interval containing those points, and the boundary of my range, okay, so the boundary that's between the points that are inside and the points that are outside, that boundary lies in only one interval, meaning I only have to recursively search in one interval. So now in 2D you could say, okay, I have a set of points, let's partition it into 2 subsets, be like here. Okay, instead of having an interval containing them, I take some 2-dimensional shape, let's say a triangle. So for both point sets I have a triangle. But now, if I do a query with a half plane, okay, so the boundary of the half plane is a line. So I would like to say, well, I have to recurse in only one of the 2 subsets. Okay, so I would like that my line only intersects one of the 2 triangles. Well, that's not going to work, right? I mean, you could be lucky that your line is maybe like this, and then I only have to recurse here. But clearly, if you have 2 triangles, no matter how you do it, there are always some lines that are going to cross both triangles. Okay, so it's basically impossible to do the same thing as in 1 dimension. Okay, so we're still going to try to do something which is a little bit similar, but apparently partitioning it into 2 subsets is not really going to work, so we need a little bit more subsets. Okay, so here's the basic concept or the basic tool that we're going to need. So you have a set of points, and now what we want to have is what is called a simplicial partition. And actually the particular conditions here, it's called a fine simplicial partition. So what is it? Well, it's a partitioning of my set into subsets, like before, but now I have more than 2 subsets. I have some, well, let's say some parameter r, and I have r different subsets. So here r is 5. For each subset, I have a triangle that contains all the points in that subset. Okay, so here you see 5 triangles, 1 for each point set. Maybe the triangles can intersect. And so this point is maybe in this subset, so it belongs to this triangle, or it could be in the other one, doesn't really matter. Okay, and I also want that each point set contains roughly the same number of points. This should be n divided by 2r, by the way. Okay, so roughly, if I have r subsets, on average they contain n divided by r points, but all of these should be, well, in a certain range. So, how was this for the binary search tree? So I had 2 subsets, and then if it's completely balanced, then each of them has, well, let's say exactly n divided by 2, or maybe round it up or round it down, so n divided by 2 points. But if you have, and then maybe if you have a red-black tree or AVL tree, it's slightly different. But why do I want to have this? Well, for the binary search tree, because I want that the depth of the tree is only log n. Right? Therefore, I want that both of the subsets are, well, small enough. So also here, I want that each of these subsets is small enough. Okay, so, this is what is a Simplicial partition. And now the crossing number is the maximum number of triangles that you can cross by any line. So here, this line, for instance, intersects 2 of the triangles. Okay. This line intersects 3 of the triangles. But I think that actually there's no line here that intersects 4 or 5 triangles. Right? If you just do it like that, then and if you think about how we're going to use it, right? Then if we do a query with a half plane where this is the boundary, let's say this line, then for all the triangles that are crossed by the line, there could be points inside or outside, so we will have to recursively search in those triangles. For all triangles like this one, or, well, if I look at this line, this one, which are not intersected, they're either completely inside or outside, so we don't have to search any further. So we want something like this where the crossing number is small. Okay, because we want to recurse in few of the triangles. So the question is, how small can it be? So here's the basic theorem. I'm not going to prove it. At the end of the lecture, depending a little bit on time, I'm going to ask you to think a little bit about whether you can prove that this is actually the best you can do. And then maybe explain whether that's the case or not. So what you can always get is that if you have, for any parameter r, okay, you can partition your point set into r subsets, each inside a triangle. So you can get a Simplicial partition. And no matter which line you take, you only intersect O of square root of r of the triangles. Okay, so you have r triangles, but you only intersect square root of r. So that's, well, fortunately not all of them, and hopefully this will give a good query time. But we'll see what happens in a moment. Okay, so what's the tree structure? I hope that you can already predict it. Okay, so it's a tree, but instead of a binary tree where each node has only 2 children, okay, I have, well, let's say the root has a child for each of my subsets. Okay, so here I have 5 subsets, so I have 5 children. In general, if you have a simplicial partition with R subsets, you're going to have R children. Okay? So at each root of the subtrees, I'm going to store this triangle. And if I want to do range counting, say, I'm going to store the number of points in the subtree. Okay, similar to if we wanted to do counting in one dimension, then for each node you had to store how many points are in the subtree. Here I do exactly the same thing. I store how many points are in the subtree. Okay, and then each of these subtrees, well, is defined recursively on the point set. So for instance, you get something like here, where maybe this node corresponded to that triangle. Then for all the points in that triangle, you take another simplicial partition, and each of the triangles in that simplicial partition corresponds to a child of that node, and so on. Okay, and this continues maybe until you have 1 point, or some constant number of points, and then you just make a leaf and you store that point. Okay, is it clear what this structure is? Any questions? No? Okay, so what's the query algorithm? Well, you come with a half plane. It's a recursive algorithm where at some point you are at a node V in the tree. H is my half plane. So if V is a leaf, well, there are 1 or maybe a few points stored there. You simply check which points are inside the half plane and which are not inside the half plane. If it's inside the half plane, you report it. Otherwise, well, you're going to look at all the subtrees. Okay? For each subtree at the root, you have stored this triangle that contains the points in that subtree. So you're going to look at that triangle. Okay, so for each of the children, you look at this triangle. Check, well, if it's completely inside the half plane. Okay, then, well, if you want to report, you report all the points, so you go down the tree, report everything. If you want to count, well, then you have stored how many points you have in the subtree, so you simply add that to the counter that you're maintaining. Okay. Otherwise, if it's not completely inside, well, then if it's partially inside, so if the line intersects the triangle, well, then you go into recursion in that tree. And the third case is, well, if it's completely outside, but then you don't have to do anything because it's not in the range. Okay, so this is fairly simple. So what about the query time? Well, it's a recursively defined structure, so we're going to write a recurrence. So here's the recurrence. If Qn is the query time, so let's look at the counting version. Well, if you're at the leaf, it's constant time. You check whether the point is inside the half plane. Otherwise, well, what were we going to do? For each of the children, okay, so I actually have R children, I'm going to check, is the triangle contained in my half space or partially contained or disjoint? So that's of R time. And then only for the ones that are partially inside, so only for the ones that are intersected by the line that is the boundary of the half space, for those you go into recursion. Okay, so, and we know that we have a simplicial partition where the crossing number is at most square root of R. So I get O of square root of R times, well, a recursive call, where I have at most 2n divided by R points. So what's the solution to this recurrence? Well, it's a little bit tricky recurrence. You can actually show that it's basically square root of n, but not quite. So if here, well, if this 2 would not be here maybe, and this big O would not be here, but I simply get really square root of r and here n divided by r, then maybe by applying the master theorem, I don't know if do you know what the master theorem is? Good. Then by applying the master theorem, you can see that you get square root of n. But unfortunately, this is not really square root of r, but a constant times square root of r. And that messes things up a little bit. So instead of square root of n, you get, well, square root n to the 1/2 plus epsilon. So what is this epsilon? Well, you can make this epsilon as small as possible, as small as you like. So if you say, I want to have Qn is n to the 0.51, okay, so epsilon is 0.01, that's possible. So how can you control this? Well, you can, or if you want epsilon is 0.0001, that's also possible. And you can control that by changing the value of r. Because, well, intuitively you would say, so the problem here is that I have a constant c times square root of r. And that sort of messes up the, well, let's say the relation between the square root of r here and the divided by r here. But the larger you pick r, the smaller the influence of this constant. And the closer you get to root n. Okay, so if you give me epsilon, then I can pick a value of r such that the recurrence solves to this thing. So let me maybe try to do on the board. So how would you prove something like this? Well, it's a recurrence, so by induction. So the claim is that, well, let me first write the recurrence again. So I have Qn is, well, if I want to do this by induction, I should no longer write big O's, but I should be explicit about the constants. So I have to say something like, okay, this is at most the constant c. If n equals 1, it's maybe cr plus c squared of r q 2n divided by r. Well, oops. Otherwise, okay, maybe I should write constant 1, constant 2, constant 3. But I can simply take the largest of the 3 and put that everywhere. Okay. So now my claim is that, well, Q is at most some constant d times n to the 1/2 plus epsilon. For d equals something, 2c, I don't know, we'll see, when I choose r large enough. Okay? And in the computations we will see how large we have to choose r. I guess I have to be a little bit Can I move this up? Is this... Ah. No, okay. Ah, okay. Yeah, I don't know. Can you see down to here, or? Ah, okay. Of course, that doesn't solve. I can write, but that's, okay. Let me just use this maybe. Okay, so I want to prove this this claim here. So I'm going to do this by induction on n. So n equals 1. Well, then it's at most a constant. So here, if I pick, let's say, d, well, if d is at least c, that's going to be fine. So I definitely need d to be at least c. Maybe I'll need some more conditions, but we'll see. So what happens if n is, so now look at n bigger than 1. Okay, so I get Qn is at most, okay, CR plus C square root of R Q 2n over R. Okay, going to use my induction hypothesis on this part. So this is at most CR plus C square root of R D 2n over R half plus epsilon. Okay. Is, well, what do I get here? I get, let's say, CR plus d n to the 1 half plus epsilon, d n to the 1 half plus epsilon times, okay, c square root of r. I still have the 2 here, 2 1 half plus epsilon divided by r to the 1 half plus epsilon. Okay? So here I have r to the 1 half, here I have square root of r. So let me, this doesn't, remove this one and here. Okay. And now what you see, so here, well, this is at most 2, so let me just replace this by 2c, and here I get r to the epsilon. Okay? So if you give me epsilon, then I can pick r large, like 2 to the power 1 over epsilon or something like this, such that this is, let's say, more than 4c. Okay? That means that this here is less than 1 half. Okay? And that means that, well, I only want to prove that this is at most d times 1 half plus epsilon. And if I have 1 half here, I have a little bit left. Right? Because this is going to be smaller than this because it's only 1 half times this. And this portion that is smaller, I can use to essentially cancel out this extra portion that I have here. Okay, so you have to choose something like, take R is something like, I want R to the epsilon to be, let's say, 4c, so epsilon is, well, log. So in the end I get epsilon, or sorry, I get R being exponential in 1 over epsilon. And R is going to be also in my constant in the bound. So in the end, let me did it switch on automatically, or did someone do this? Okay. I thought it was a very advanced system. Good. I guess it will stop. No, not really. Okay. Okay, so you can get this epsilon as small as you want by choosing R large enough. R is still a constant, right? Because epsilon is a constant, like 0.01, and then R will be a constant, so that's fine. But this constant is going to show up here. So in practice, choosing a really small epsilon is probably going to give you a huge constant. So that's maybe not so nice. But in theory, this is what you can get. So that's also, if you read lots of papers on computational geometry, have these bounds that have an epsilon. So this is, typically these are things that are using partition trees or something, and this is how you get this epsilon. Okay, so how much space would this thing cost? Well, we can do it in the complicated way. Namely, it's a recursively defined structure, so let's write a recurrence. So if I have 1 point, I have a leaf. Otherwise, well, for each of my triangles, I'm storing the triangle. And then I have the sum over all the children of, well, the storage needed for that subtree, where, this is the number of points in this subset for the child W, and I know that every point goes exactly to one of my subsets, so the sum of these things is n. Actually, later when we do more complicated things, we will need this recurrence, but now there's actually, I simply have a tree. Right? It's not a binary tree, but it's a tree where the number of leaves is the number of points, so it's linear size. Right? So, we just have a tree with n leaves, and for any tree, it doesn't really matter whether it's binary or has 5 children or whatever, the number of nodes is always linear. Right? O of n. Okay, so to summarize, if you have a set of n points in the plane, then for any epsilon, 0.1, 0.001, you can construct a data structure that uses linear storage and where you can answer half-plane range queries in basically square root of n time, or maybe n to the 1/2 plus epsilon to be precise, where this epsilon you can make as small as you want. So I'm not going to explain, but you can actually also quickly construct it. Then you have to, the difficult step in the construction is to actually compute the simplicial partition. Okay, because after that, compute the simplicial partition, then, okay, for each triangle you have a subtree, you recursively construct the subtree, so that's easy. But computing the simplicial partition is actually complicated. So there are lots of fine-tuning you can do, that you can actually make sure that the query time, that this epsilon goes away. If instead of counting you want to do reporting, okay, so here what you can say, well, use this structure, and whenever you have a subtree that is completely inside, just visit the subtree and report all the points. So reporting would be n to the 1/2 plus epsilon plus the number of points. But actually for reporting you can do much better than this. You can essentially get log n plus the number of points. But for most applications that solution is not very useful. So for instance, what we will do tomorrow is, instead of searching with a half plane, let's say you want to search with a triangle. Then even for reporting you have to use these techniques. You cannot do this other thing. So this other is really special. It's for reporting, and it's for half plane reporting and not for anything else. And this you can apply to many different settings. Okay, so this is pretty, well, the storage is nice, but it's very slow. Well, it's square root of n plus this epsilon, which in practice, because of the constants, is maybe also a problem. So the question is, in 1D we could get log n query time, so why not in 2D? So actually it turns out that it's possible to do that, but we will pay for this in terms of storage. So let's see how we can do that. So I think the past few days somebody talked about duality. So let me very briefly remind you how this works. Okay, so this is the space that we have, our primal space, and now what you're going to do is a mapping from this two-dimensional space to another two-dimensional space, which is called the dual space. And if I have a line here, it will go to a point here, and if I have a point here, it will go to a line here. And up there you see what the mapping is. So if I have a point px, py, then the line that it goes to is, well, you see the equation, y equals px times x minus py. And if you have a line, it goes to that point. Okay, so what are the important properties? Well, as you can, so for instance here you see this is the line y equals, what is it, x plus 1, so that will go to the point 1 minus 1. So the important property is that if, let's say, this point Q lies on this line L, then here the point L star, so the dual of that line, lies on the dual of that point. Okay? And also if this point lies below this line, then here this point lies below this line. So it's called, well, it's incidence preserving. So if you have an incidence, a point being on a line, then in the dual space you have the line containing the point. Okay? So point on a line, here point on a line. And also it's order preserving. If this point is below this line, then the dual of this line, which is a point, is below the dual of that line. So now we're going to look at half-plane range searching in dual space. So I have a set of points, and I want to, let's say, count the number of points below a line. Okay, so what happens if I look at this in the dual space? Well, instead of a set of points, I now have a set of lines. And instead of all the points below the line, I want to find all the lines actually above a point, right? Because this point is below this line, meaning that the dual of this one below the dual of that point. Okay, so I have a set of lines, and the query now is I come with a point, and I want to, let's say, count how many lines are above this point. Okay, so let's see how we can do that. So what we need here is something which is well, you could say for points we had these simplicial partitions as the basic geometric tool. So here we need what are called cuttings. So I have a set of lines, and now I have a 1 divided by r cutting. And r is again some kind of parameter, a number. Okay, so it's a partitioning of the plane into triangles. So here, this is one of my triangles, this is one of my triangles. Some triangles are maybe unbounded. They have 3 sides, but it goes to infinity. And the property is that each of these triangles is going to intersect only, well, not too many lines. So if I have a 1 divided by r cutting, it should not intersect more than n divided by r lines. Okay, so you can imagine if these green triangles, if you make them really small, then each triangle is intersected by only maybe 2 or 3 lines or something. But if you make them really small, you need lots and lots of triangles. Okay? And so here what I want is, I want to guarantee that each triangle is intersected by only n divided by r lines. But I do not want to use too many triangles, right? If I make them, like I said, if I make them really small, then I can probably easily achieve this, but maybe then I have lots and lots of triangles. So the question is, how many triangles do you need to have this guarantee on this number here? Well, and here's the theorem. You can do it with r squared triangles. Okay, and again, well, at the end, maybe this is actually not too difficult to see, that you cannot use really less than r squared triangles. But you can think about that later. So I have this partitioning of the plane into triangles. Now I've omitted all the lines and just look at the lines inside one of these triangles. So there are not too many, at most n over r. Okay, and you can always do this. And you can also compute such a cutting quickly. So now, how would you set up a data structure such that if you can quickly count how many lines are above that point? Okay, based on this. So we're going to have a tree. Okay. What are the children of our tree? They correspond to triangles in the cutting. Okay. So it looks like this. I have this 1 divided by r cutting. Okay. For each triangle, so for this triangle, for instance, I have a subtree here. So I have a child wi for each triangle delta I. Okay. So now imagine if you do a query and the query point is inside this triangle. Okay. You have 3 types of lines. The ones that are above the triangle, the ones that are below the triangle, and the ones that go through the triangle. Okay? Only for the third type, you still don't know whether it's above or below. Okay? The other ones, well, the ones that are above the triangle, like these red lines, they are definitely above the point inside the triangle. The ones that are below, they are never going to be above that point. So if I want to count how many lines I have above the triangle, then, well, if I just want to count, then I would store, I look at all the red lines, so the lines above this triangle, and I would just store, let's say, how many of them I have, just a number. If I would want to report them, maybe I actually have to explicitly report or store this set of lines. Okay, so here I store the triangle plus, let's say, the set of lines that are above. And then well, this is the root of a recursive structure for the lines that go through the triangle. Okay? So, how do you answer a query? Well, again, it's a recursive algorithm. You get to a node V with your query point Q, so the red point. Well, if V is a leaf, you have one line, you just check if it's above or below the point, and then you can maybe you report it if it's above the point. Otherwise, well, you have all these triangles of your 1 divided by R cutting. You simply look at all these triangles to find the one that contains the query point. Okay, so find the triangle that contains the query point. Well, that corresponds to a node Wi. Now, with that node, you have stored all the lines above the triangle. So you simply report all of them. Or if you want to count, you just add the number to your counter. And then you go into recursion in this subtree. Okay, so the crucial difference between this one and the partition tree is that here you only go into recursion in one subtree. Okay, because my query point is inside only one triangle. For the partition tree, you had all these triangles and the query was a line, and you have to go into recursion in all the subtrees where the triangles are intersected by the line, and there could be many. Right, for a partition tree, square root of R. Here, the query, we're now in dual space, the query is a point and it lies inside exactly one triangle, and that's the only subtree that you have to go into recursion. And therefore the query time will be much faster because you only go a single path down the tree. Okay, so what's the query time? Well, if you have a cutting tree with n lines, well, when you're at the leaf, it's constant time. Otherwise, well, you simply check all the triangles to see in which one is my query point. Okay, I have R squared triangles, so that's going to take me R squared time. Then, you add the number of lines to your counter, and you recurse into only one subtree.
I don't understand how we construct a tree. In each node, we have the lines which are above that triangle, and the parents of each node is what? No.
Okay, so let's see. Here. Okay, so initially you take your set of lines, you construct this cutting. Okay, you get a lot of triangles. For each triangle you have a child of the root. Okay, so each of these triangles is going to be a child of the root. I store with that node exactly as you're saying. For each triangle, I look at all the lines which are above, and I store that set with that node, and maybe also the size of the set in case I want to do counting. So it means that these lines, so this line, for instance, is going to be stored at many nodes, right? Because it's above this triangle, but the line is also above this triangle and this triangle and this triangle. So I have lots of these sets, one for this node, one for this node, one for this node, one for this node. So there, and a line is going to be stored in many of those sets. Okay? And then for, let's say, this node corresponding to this triangle, I'm going to have to recursively build a structure on all the lines that intersect the triangle.
Triangulate each triangle.
So indeed inside this triangle, so let's see. Okay, so I have it's also green. That's good. Okay, so I have some triangulation, oops, and so on. Okay, so let's look at this triangle. Okay, I have lots of lines that cross this triangle. Now in recursion, I'm going to build, well, let's say another cutting. Each of these triangles, like this one, okay, is going to be, well, I had my root, I have lots of children, maybe this WI corresponds to this delta I. Okay, each of these triangles, this one, will be a child of this node. Yeah? Okay.
We have a query point inside the triangle. Let's consider a semisecond starting from this point to above the plane. Up to the point. So we count the number of intersections of triangle and this semisecond. I'd like to know if we can have it bound on the number of triangulation that intersects with that semisecond. We had a square root of r for the number of infinitesimal points.
Okay.
Do we have any kind of restriction, any kind of bound for this?
So you mean if I have, let's say my query point is here, now I look at this line, and it's going to intersect this triangle and this triangle and this triangle, and you want to know, is there a bound on how many you intersect? No. But we don't need that because we already store, even if there's lots of triangles above here, I'm going to I store all these lines here, right? So you could imagine that maybe you can somehow be a little bit more space efficient by not storing it and looking at all these triangles above and somehow collecting the lines from there, but that's not what we do. So
instead, how can we, after we report the query, we report the answer of the solution of our problem, we apply that we have n over r number of lines that intersect each triangle. After we count the number above the query point, can we report the number of triangles? We have a bound on each triangle about the number of lines, and after when we query the point.
yeah, so we don't know anything about the number of triangles, but that's also, I mean, the triangles are just, they're not part of the data, right? It's something that we constructed. So the number of things above the query point is also, well, let's say the user would not be interested in that because he wants to know about the data, about the lines. So, okay, so, well, I hope that now the construction is clear. So the query time, so this was the query time. So what's the solution to this recurrence? Well, it's just going to be log n, right? For instance, even if I take r equals 2, right, then here I get O of 1 plus q n divided by 2. Okay, so it's log n. If I take a larger r, that's basically only going to be better because, well, this is going to go up a little bit. But here this is going to go down more rapidly. Instead of n divided by 2, you get n divided by 10. So for any constant r, this is going to be log n. Okay, so that's nice. So what about the amount of storage? Well, again, at the leaf, well, I just store the line. Otherwise, I have r squared triangles. Okay, for each one of them, I store, like for this triangle, I'm going to store all the lines above it. These red lines in the previous picture. Also there. Okay, so, and there could be all of them at most. So r squared times n. For each of my r triangles, I'm going to recursively build a structure on n divided by r points. Lines. And, well, again, you get, if there's no big O here and you get r squared and here n divided by r, it would solve to exactly n squared. But since I have this O here and this constant, it's actually slightly more than that. And again, if you give me an epsilon, I can pick a large value of r such that the solution is n to the 2 plus epsilon. Okay, so here's the summary. For any epsilon, you can get a data structure that uses n to the 2 plus epsilon storage, and now the query time is only log n. Okay, so what did we see? Well, if you want to do this half-plane reporting, so you can either get, if you use a partition tree based on Simplicial partitions, you get linear storage, which is nice, but the query time is square root of n, or slightly more, n to the 1/2 plus epsilon. If you apply duality and then work with these cuttings, the query time is only log n, which is very nice, but the storage goes up to n squared. Okay. So one of the things we're going to look at tomorrow is, well, or Wednesday, I don't know, is suppose you want to do something in between. Right? Maybe you don't really want to use n squared storage, or a little bit less, n root n or something. Then what can you get? So, as I said, all of this also works in high dimensions. The ideas are exactly the same. So I have a set of points. You also have something which is called a simplicial partition. Okay, so you partition your point set into subsets. Now for each subset, you don't have a triangle containing all the points, but let's say in 3D you would have a simplex. It's like a pyramid containing all the points. In higher dimensions, a higher dimensional simplex. Now you look at how many of these simplices are intersected by a plane in 3D. Okay. Now you cannot get square root of r, but you will need r to the 2/3 in 3 dimensions, or in 4 dimensions r to the 3/4, and so on. And then the query time will be, well, n to the 1 minus 1 over d. So for d equals 2, you get 1 minus half, so you simply get a half. For d equals 3, you get 2/3, and so on. So the higher the dimension, the closer you get to just linear, right? Which is natural. The higher the dimension, the more difficult it becomes. Okay. Also for these cutting trees you can get what, you can generalize to higher dimensions. So instead of this cutting again works in the same way, you have a set of planes, let's say in 3D. You partition your three-dimensional space into regions that are maybe again simplices. Every simplex is intersected by only n divided by r planes. Okay? So that means that if you do a query, well, you find out in which simplex you are, you go into recursion, and then since you have only n divided by r things going through, you get exactly the same recurrence for the query time. So it's still going to be log n. But the number of simplices in the cutting, so for 2D we had r squared, now you get r to the power d, and as a result the storage goes up from n to the 2 plus epsilon to n to the power d plus epsilon. Okay? So maybe at the end this... okay, so these were the tools, and they also generalize. Let's maybe spend a little bit of time, because there's a little time left, thinking about this. So I give you a few minutes to think about this. So what you have to think about is these two statements. Okay? So here we said that for any set of points, okay, you can partition into subsets, for each subset a triangle, such that you intersect square root of r of the triangles. So the question is, can't you get, I don't know, something smaller, maybe only log r triangles, or n to the 1/4 or something like that? So the exercise would be show that this is impossible. That's, if you see I will explain in a minute, so you can think about it, but that's actually not that easy to see. This one, okay, so here I have a set of n lines. I want to partition the plane into a number of triangles, and the condition is that every triangle is intersected by only n divided by r lines. So my claim is that you will need r squared triangles. You cannot do it with r triangles or r squared of r. So think about this. This is actually the easier question of the two. So if you think about it, maybe a few of you will actually come up with an argument that this is the best you can do. So maybe first think about this one. If you solved it, think about that one. So I give you a few minutes, and then you can discuss a little bit, and then I will explain why these things are optimal. So did someone already came up with the argument? Yeah, it's one of these things where if I tell you the argument, then you'll say, ah, yeah, of course. But it's not too easy maybe to think about it. So if I have, let's say that this is my 1 divided by r cutting, I don't know, and so on. Okay. So let's say if I look at one of these triangles, okay, how many lines are there in here at most? Well, n divided by r. Okay, so here I've, by definition, at most n divided by r lines. So how many intersection points can you have? Well, if I have this many lines, then at most this many intersection points. Or maybe I should actually write n over r choose 2 or something. But definitely at most this many intersections. How many intersections do I have in total? Well, n squared. So in total, n choose 2 is, well, intersections minus whatever 2 so if I have, let's say, roughly, if I have n squared intersections and I can have only n squared divided by r squared in each triangle, well, somehow I must have r squared triangles, because all these intersections must be somewhere. Okay, so this is pretty easy once you see the argument. So as you can see, this actually doesn't really depend on which set of lines you have. For any set of lines, you can do this argument. Well, so normally a set of lines has n squared intersections because any two lines intersect. If all the lines are parallel, for instance, then it's different. Of course, if they're all vertical, well then, you could have a cutting which consists of essentially vertical, long vertical triangles or something like that, infinite triangles, and then you get something better. But as soon as you have the set of lines is what is called in general position, so any two lines intersect and all the intersection points are different, so sort of the normal case, then, well, you have n squared intersection points, so you need r squared triangles. Okay, so that shows that indeed you cannot do better than this. So here, this should be r. I should change my slide here. So maybe I can write. Here, actually, for some point sets, you can do a lot better than this square root of r. So let me give you an example. So let's say my point set looks like this. I take, I don't know, any convex curve, parabola, or something like this. And my points are simply going to be here. Okay, and so on. And now what I can do is something like my triangles here. Okay, so I have R triangles. But if this is really in a convex position and this is really flat, then a line is going to intersect, well, it's going to intersect the convex curve at most twice. So it's also going to intersect maybe at most 2 of my triangles. So actually for some point sets you can do a lot better than the square root of R. And if you're looking for a very difficult open problem, then what you would like to do is compute a simplicial partition. So what we know how to do is compute a simplicial partition where this crossing number, so the number of triangles intersected by a line, is always at most square root of R. Okay, so maybe here it's also square root of R, because our algorithm is not doing this but something else. So what you would like to have is maybe that the crossing number is actually optimal for the specific set of points, so that if you get this input, you will get this with maybe crossing number 2. If you have a very difficult set of points, maybe you get crossing number square root of R. If you have another, maybe you can get crossing number, I don't know, log R or something like that. So if you, and it's unknown how to do this. I think it's probably NP hard, so maybe you can get some kind of approximation algorithm. But let me, maybe to finish off for today, explain that at least for some point sets, you will need this square root of R. And the point set is very simple. Namely, I'm simply going to put my points on the grid. Okay, so this is my point set P. So this is a square root of n by square root of n grid. Okay. And, well, now you can come up with some kind of simplicial partition where you say, okay, maybe, I put these things together and these and so on. So this could be maybe one subset, this is another subset. And I claim that no matter how you do it, I can always find a line that intersects at least square root of R of your triangles. Okay? And it's actually a very nice argument. And the argument is the following. So look at the following. I'm going to put a number of vertical and horizontal lines like this. Such that, let's say here I have, I don't know, roughly, let's say square root of R divided by 2 points, or rows, and here I have, I don't know, maybe square root of R rows. Okay, so actually the way I've drawn it is maybe not quite. Okay, so how many points are in one cell? Well, this divided by this, R over 2. Okay, so I've here R divided by 2 points. Okay, so what does it mean? It means that all your wait, no, did I do it? Sorry, I picking my, so what I want here is, let's say, n divided by let's say 4r. So I have to change this. So this is root n divided by r, root n divided by r. Okay? So here I have n divided by 4r points. So in your triangles, there should be more than this many points, because you should have at least n divided by 2r points. So that means no matter how you pick your triangles, every triangle has to contain points from at least 2 of the cells. You cannot have a triangle that is completely inside one of these cells. So your triangles, they must look something like, I don't know, maybe some points here and then also some points from some other cells. Okay, so every triangle that you pick, it must contain points from more than one cell. That means that every triangle is going to be intersected by at least one of these lines. Okay? So now let's see how many lines do I have. Well, here I have square root of n points. I put, let's say, square root of n over r. So here I have something like roughly square root of r lines, or maybe 2 times square root of r lines. Okay? Here, the number of these lines is also this. So in total, I have total number of lines is, let's say, 4 times the square root of r. Okay? So you give me any simplicial partition. Every triangle in your partition will be intersected by at least one of these 4 times square root of r lines. Okay? How many triangles did you have? You have r triangles. Every triangle is going to be intersected by one of my 4 times square root of r lines. So one of these lines must intersect at least square root of r divided by 4 of your triangles. Right? I have you have r triangles, let's say 4 square root of r lines. Okay. Number of triangle line intersections is at least r. Right? Because I said each of your triangles is going to be intersected at least by one of my lines. So if I count the number of times a triangle is intersected by a line, in total this is at least r. Well, if I have only 4 times square root of r lines, well, the average line actually intersects r divided by 4. The square root of r is 1/4 r line. So of these lines, the average number of intersections is this. Oops. So one of them must actually intersect so many. So no matter how you do it, you're always going to get a crossing number, which is at least this. Okay, so well, that shows that these tools that we're using are optimal in a sense. You cannot do better. And actually also these results are best possible. If you want to use only linear storage, you can prove that no matter what kind of data structure you use, for half-plane range counting, the query time must be square root of n. And if you are, if you want to have log n query time, you must use n squared storage. So up to these epsilons, it's possible. It's optimal. Okay. Are there any questions?
In Katrina, we know we use that we cut the area with triangle. Can we cut the area with, for example, squares? And I think the proof will be okay there.
So in general, using squares, so it's okay if you use squares, but then it's not always possible to get the same bounds. So you could, it's slightly easier to see if you think about the simplicial partitions. So there, instead of triangles, you could also use squares. But for instance, if your points look like this, then the best thing you can do if you have squares is to do something like and then actually all of them are going to be intersected by this line. So you cannot get a crossing number which is square root of r. This also shows a slight technicality which I didn't mention, namely that here, if these are really on a line, then, and I take this line to go exactly through these points, it's always going to intersect all the triangles. But in that case, this triangle here will degenerate to a one-dimensional line segment. And what you're counting for the line segment is a line that really crosses it and that not containing it. Because also if it contains it, you already know that everything is in the half plane when it's a closed half plane. So a similar argument you can do here, that if you insist on using squares, then you cannot always do it with r squared squares, and that each square is intersected by only n divided by r lines. So if these lines are somehow strange, then you need the flexibility of different orientations that you can get from the triangles to make it work.
But every intersection points of two lines will be exactly one square.
Yeah. So you're right that the lower bound proof works just fine for squares. Yeah.
I'm really curious about how we triangulate between r cuttings that each triangle contains n divided by r line. This seems to be a complex issue.
Okay, so I can, but maybe then we should go for the break, and you can actually ask some questions during the break. But let me just in 1 second explain the easiest way to do it. So you have a set of lines, and now I want to find this cutting. So I want to partition the plane into triangles. So one way of doing it is to take a random sample. Okay, so take random sample of the line. So I randomly pick of size r. So I randomly pick r lines. Now each of the cells I partition into triangles, maybe like this. Okay, now everything is a triangle, or at least bounded by 3 sides. Well, actually, sometimes maybe you have, if I have 4 sides, I can triangulate like that. And now you can prove that the expected number of lines passing through one of your triangles is n divided by r. So a simple way to get, and that proof is not easy. So a simple way is take a random sample and then triangulate the random sample, and then you have your cutting. It's a little bit tricky, but this is basically the idea. There are also ways to do it deterministically, but it's... So, good time for a break, I guess. So if you have more questions, then you can ask me during the break.